How many plus? 1 plus 2 plus 3 plus 4? 4 plus? How many minus? So now you guys get me confused. Let's start about today's lecture. In the past two lectures, we talked about tools in Laplace domain and in Z domain to handle continuous time signals and discrete time signals. Specifically for the Z transform, we introduced this definition how the time domain sequence, discrete time domain sequence, can be transformed into the Z domain by summing out over K, the time index. Now, this new quantity in the Z domain has many similarities in terms of the continuous time domain relationship. We see the impulse also corresponds to 1 in discrete time sequence. And the geometric sequence, AK, 1 of K, this is sort of like the e to the negative at in Laplace case. So it's 1 over 1 minus a z to the power of negative 1. Or if you prefer, you can write it as z over z minus a. We did in class how to do the cosine case. Cosine omega 0k is a second order function, rational function of z in the Z domain. So it's 1 minus z to the power of negative 1 cosine omega 0, 1 minus 2z negative 1 cosine omega 0 plus z to the power of negative 2. These are the common useful pairs of Z transform. Some properties that are very handy are if you delay or advance in time about a sequence, then the Z transform is very easy. If you delay here, negative 1 is z to the power of negative 1. If you plus 1 here, it's z to the power of plus 1. If it's negative n, delayed by n steps, is z to the power of negative n. And the difference is just a few additions, a consideration of the initial condition. So for one step delay is plus, you need an extra step looking back of f to the power of negative 1. If it's 0 initial condition, if we assume all the sequences are causal, meaning that it's 0 for negative time, then these two equations are significantly simplified. You just need to focus on this part. So very simple. If it's one step advanced, you need to be a little careful if the initial condition is not 0. So that's how it relates. We discussed how to derive them in examples and exercises, which is what we're going to do in a few more minutes today. But we also discussed partial fraction expansion in the Laplace case. So if you have 1 over s plus a times s plus b, then partial fraction expansion can help us decompose the big one into two smaller modules. And the coefficients are very easy to compute as long as you understand the mechanism, how the method of undetermined coefficients work. So the formulas are K1 is take the limit of s equal to negative a, and then this whole quantity multiplies s plus a. So this one gets cancelled out. You are left with 1 over s plus b. Same thing for K2. And then we talked about, in Laplace domain, the concept of DC gain, what that means, which we'll revisit and enhance our understanding in the discrete time domain today. Any questions? All right, cool. Let's take a look at the example. We have this discrete time system, input and output. The initial condition is 0, and the input is a step function, 1 of k. So last time we talked about, we derived the transfer function, and we discussed the step function, the Z transform, is using this formula precisely, a equal to 1. So we figured out how y looks like in the z domain. So here now we're doing this step. How do we go from here to here with partial fraction expansion? So it's a little bit different from Laplace domain, if you notice. What is the difference in this case compared to what you see on the whiteboard? Say that again, please.
It's like b to the negative 1 power.
So you're talking about this one, how we write it here, right? So these, you can understand z transforms in two ways. The first way is you use the notation of z to the power of negative 1. And then the second is you use z instead of z to the power of negative 1. There are subtle differences about how you use partial fraction expansion for these two cases. Now, if I want to use directly partial fraction expansion, what should suppose this is z. Then you can notice the difference here. If you want to use partial fraction expansion directly using this formula, using these two formulas, then the numerator should be 1, which is not the case in this example. Numerator is z, right? But it should be no problem. We can easily do what? We can factor out the z, right? And then use the formulas immediately. So be a little bit careful about how you use the partial fraction expansion. So what we do, the full procedure is we factor out this z, and then inside we have a perfect formula for partial fraction expansion. So we can let it be k1, z minus 1, k2, z plus 2, and k3, z plus 1. So you get the idea. And then you can use the formulas for k1, k2, k3. I will just do k1, and you will finish the remaining k2 and k3. k1 should be the limit, letting z to be 1. And then inside is z minus 1 times this whole item. So it's going to be limit z to 1, 1 over z plus 2, z plus 1. So that is how z1 should look like. And if you evaluate, it's going to be 1 over 3 times 2. So it's 1 over 6. That's k1. Which is what you see here. This is exactly k1. You can do the remaining for k2 and k3. Now, after this step is done, then all these are very familiar to us. This is precisely some modification of this formula. So it's going to be a geometric sequence, ak. So the difference is what is a here. If I take a look at z over z minus 1, a is 1. So the first component of yk is going to be a step function. A is 1, so it's yk. It's 1 of k at the bottom, the first component at the bottom equation. And then the second would be a is negative 2. So the second component should be negative 2 to the power of k. And the last component is a is negative 1, right? So it's negative 1 to the power of k. Precisely what you see here. The three items here. You should be able to derive k2 and k3 using this logic over here. All right, let's take a look at an application of z-transform. So we talked about annual percentage rate, how your money increases in the bank. Suppose a similar related problem. Suppose you borrow a certain amount of money from the bank, let's say 100,000, and you needed to pay back the bank, not immediately, but let's say through 30 years. So the bank will give you an annual percentage rate, let's say 4%, and you want to pay in 30 years. And you want to pay a fixed amount monthly just to make your life easier. The interest is going to be computed monthly, and we wanted to know what is our monthly payment. Obviously, this is a discrete time mechanism. You pay month by month. So let's translate the language into a system language. We try to model how the payment looks like. So borrowing 100,000 means that you're going to need to pay back eventually 100,000, right? As you pay more and more monthly, your remaining debt is going to be less and less. And you have an annual percentage rate of 4%. That means monthly you need to pay, the monthly percentage rate is 0.0033, just division by 12. So this is the interest rate you're paying monthly. So you want to pay how many months within the 30 years? It's going to be 30 years times 12. You're going to pay off in 360 months. That means at the end of, so let n equal to 360, then at the end of this 360 months, you don't have any, you paid off. You don't need to pay anything. So your debt is going to be 0. Here is how it looks like in equations, in formulas. Your remaining amount of dollars you need to pay is going to be dependent on how much you pay monthly, as well as how much the remaining debt, like in the last month, how much you have left in the last month, times the 1 plus the interest rate, the monthly percentage rate. Let's denote it as A, and this is the monthly payment B. I'm paying it like constant. Every month is the same dollar amount, so B is a constant. Take a moment to digest this model over here. What you're left with depends on how much you have to pay, the total amount you have to pay right now, minus what you want to pay this month. And then there is an interest rate. The more you have to pay, then this remaining, so the more yk is, then the more yk plus will be. So initially, your yk is going to be a large. Y0 is a large number, and then your remaining amount you need to pay is going to be the initial dollar amount minus the first month. The procedure iterates itself. Once this step is done, then the tool of the transform can be used to find out the solution. All right, so you have the strategy, right? You can pay significant amount of dollar at the beginning. Let's say I pay off. In the first month, I pay 100,000. Then I'm not paying a lot for the interest. And the less you pay here, then this part, the contribution from the monthly percentage rate is going to be large. Once this is done, then we can see this is nothing but a discrete time sequence. And the input is 1 of k, but we don't know how much we should pay. We don't know the coefficient yet. We want to identify what is the best number to put here so that I can pay off exactly in 30 years. So we can do Z transform. It's going to be Z transform Z y of Z using the formula over here minus Z times the initial condition equals, on the right hand side is going to be A y of Z minus B times the Z transform of a step function, which is going to be 1 over 1 minus Z inverse. We can do the usual thing, combine the term about y and then shift all the other terms to the right. So we're going to get Z minus A y of Z equal to ZY0 minus B over 1 minus Z inverse. And then divide both sides by Z minus A, we get YZ equals Z over Z minus A times the initial condition minus B over, should be minus B divided by 1 minus Z inverse divided by Z minus A. The first term is easy enough. This is a first order Z transform. So this is precisely using the formula on the board. This is a geometric sequence. So it's going to correspond to AK y of 0. The second term is a second order term, and we can use partial fraction expansion again to derive the two modules. The result is over here, B over 1 minus A, 1 over 1 minus A Z inverse minus 1 over 1 minus Z inverse. So take a moment to check these two. Okay, you guys got it? So let me ask you a question. Here, we identify this as a typo. Now, is this typo carrying over to here or not? So if you were able to do this partial fraction expansion, you should be able to tell me whether this is plus or minus. Anyone?
Should be minus.
Should be minus, so there's a minus. Any other proposals? How many of you agree it's a minus? How many of you think it's a plus? Oh, there's a plus, plus. Anyone else? So the remaining, you're not sure, I guess. So let's do this. Let's do this together as an exercise. Actually, it's worthwhile to, I'm going to do it on this side so you guys can always see. So this is partial fraction expansion for discrete time systems. So as example, this is what we are given. 1 over Z minus A be 1 minus z inverse. So let's do the approach that we mentioned earlier. I know how to do partial fraction expansion if it's something that looks like this. So if I know this is S, then it's very easy. This is what we did in continuous time system. So I'm going to use the notation of Z. So over here, we know how to do the partial fraction expansion if this is Z minus A, Z minus 1. We should be able to do partial fraction expansion for this one just using the formula on the left-hand side of the whiteboard. Any questions up to here? Okay, let's work on this one. So this is V. I'm going to try to decompose it into two smaller modules, K1 and K2. This is exactly like Laplace. If you treat this as S, 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 this is the same. Everything is the same in Laplace case. So K1 should be what? K1 should be limit Z go to A, Z go to the roots, and then the whole thing multiplying Z minus A. So it's B over Z minus 1, which is B A minus 1. So what is K2? Similarly, I don't have the space here, but it's same logic. It's limit Z go to 1, and then this whole thing multiplying Z minus 1. So it's the limit of B divided by 1 minus A. So I'm considering the B here in this calculation, so I don't need this B in the front. So the B is already considered in calculating K1, K2. So therefore, the whole second order Z domain transfer function is two modules Z times K1, which is B over, I'm going to use 1 minus A, B over 1 minus A times Z minus A, and then a negative sign. So it's A minus 1 here. I use 1 minus A, so there should be a negative sign here. And then for the second term, it's going to be B, the second term is here, the K2 is here. Second term is B over 1 minus A times Z minus 1. Any questions? So what is the sign over there? Now you guys can tell me what is the sign?
Plus, I think.
Plus?
Yeah, minus, negative, plus.
How many plus? 1 plus, 2 plus, 3 plus, 4, 4 plus. How many minus? So now you guys get me confused. Well, what's the remaining students confused about? So I got the coefficients in the front.
Right, so he pulls negative out, then it will be the bracket K1 minus K2. And K2 right now is a positive, and K1 is negative comes out. Negative of K1 minus K2. This work because I need a different substitution. I just assume that.
Yes? Questions?
And I saw C no.
Because you had a negative sign up there, and then it's times the negative c. So then it becomes positive. And the second term is negative.
All right. Looks like some of you are nodding, so you guys figure it out. Plus or minus? Plus?
Yeah.
Plus? Sure? Plus, plus? All right. So, that's not a controls problem. That's just a single sign problem, right? The key point I want you guys to make sure is to be able to go now from here to here. So therefore, this one is a geometric sequence. This is a geometric sequence. This is a to the power of k, and this is just a step signal. This is 1. So that's the formula. So now let's make some sense out of the formula by trying to see whether we can achieve zero debt at the 30 years mark. We want y of n to be 0. So we want let k equal to n. It's going to be a n y 0. So this whole thing needs to be 0. So this should be equal to negative b over 1 minus a n minus 1. So let's see whether this makes sense, right? If the sign is not correct here, you're going to get some not possible numbers. It's giving us, we want to be able to determine what is the monthly payment, so we want to know b. So b from here, from this equality, b should be am y0 times, I have a negative sign here, so it's a minus 1, right? Divided by an negative 1, an minus 1. What's the value for an? Is it larger than 1 or smaller than 1? Larger than 1? A. Larger than 1. So a minus 1 is positive, an minus 1 is also positive. So the whole thing is positive, right? So this is some reasonable number. You pay 477.42 monthly for 30 years in order to pay off this one. So which is about correct. If you guys ever buy a car and know how much you pay monthly to buy off a car, this is about the number. So a car, let's say 20,000 or 30,000, you pay off, if you pay monthly by this number, you can pay off in 2 years-ish. So it's really a handy tool once we figured out the physics, figure out the model, then Laplace and Z can be useful formulas. We did a first order example. The mortgage example is a first order system. It's the same logic if you have a nth order system, yk, an minus 1, yk minus 1, all the way to yk minus n. Your output can depend on previous input in complex linear combinations and complex linear combinations of the input. Then Z transform is very useful. It can simplify the model quite a bit by expressing out what u and y are related by this Z transform property, which is the discrete time transfer function. So nth order in the output, if your output depends on all the way back to km minus n, you got a nth order polynomial of z in the denominator. Same thing for the numerator. So this looks simple. This looks close enough to a transfer function in S domain. So let's take a look at how these two can compare to each other and what are the common language and characteristic of these two will look like. So we're going to talk about poles, zeros, and DC gains. In continuous time, you get differentiation. In discrete time, you get delay or time shifts. We can think about these two and recall in continuous time we got poles are the roots of this denominator, zeros are the roots of this numerator, so the same thing happens to here. You can calculate the poles from the denominator in the discrete time domain. You can calculate the zeros of the numerator for this transfer function. We require the denominator order to be larger than or equal to the numerator's order for GS. We do the same thing for GZ. Based on the same logic, you can see if, let's say, this is violated, let's say n is 0 and m is 1, what will happen? If n is 0, then it's going to be yk equal to bm is 1, b1 uk plus 1 minus 0 plus b0 uk. So immediately this is not causal. You are using the future information for your current output. This is causality condition. Now what I want to talk about a little bit more is the DC gain concept. In the continuous time case, we talked about the concept of DC gain, which is G, the transfer function evaluated at S equal to 0. And we obtain that concept by thinking about what happens after everything converges. If y goes to some constant in the end, then all these derivatives are going to be 0. Same thing for u. So all these derivatives are 0. So we have a picture over there, which is typical on the right-hand side of the whiteboard. If you have a step function, it's very easy that your actual response will go through some transient and then go to some constant. The ratio between these are the DC gain. Now, what is the case for the discrete time system? If y at the end is a constant and u at the end is a constant, what will happen to these elements? Yk and yk minus 1, they are going to be the same if time is large enough and they are constant, right? So all these are going to be the same constant. This is equal to this. This is equal to all the way back to yk minus 1. You can take out this constant. Take it out. So for this one, you're going to have y at the end times all these coefficients, 1 plus an minus 1 plus a0 in the end. And then on the right-hand side, it's the same logic. Time is large enough, and it's a constant. So you can do u infinity bm minus 1, and b0. The ratio, you can see immediately what is the ratio. Y infinity over u infinity is going to be this number divided by this number, which is what? This transfer function evaluated at z equal to 1. So it's no longer 0, but it's 1. That's the DC gain, direct current gain. Questions? I'll add this result here. So for discrete time systems, you're going to have, let's say, UK, GZ, and then YK. So this time it's a discrete time sequence. And the output is going to be something that looks like this. So the DC gain, the main message, DC gain equals, which is what happens here. If this is 1, then this value, this is the DC gain. And it equals G1. So you can think about the extreme case. The extreme case is, let's say, G is a scalar, K, right? So extreme case, G is just going to do scaling up my input. So it's immediately, you can see that this equation is valid. If GZ is K, then obviously the DC gain is K. It's just a scalar. And K equals G1. So we already talked about some of the helpful properties for Z transform. This is a more detailed slide about some of the most useful properties for Z transform. Time shift, we already talked about it. If you delay by n step, it's going to be negative nd here if the signal is 0 for all negative time. And if you scale a time sequence by ak, then it turns out the Z domain is going to be scale the Z by a to the power of -1. Differentiation in Z. If you have, so recall, if we have t times ft in Laplace domain is a differentiation in S domain. Same thing is the differentiation in Z domain for if you scale the sequence by time. There is a Z here, just coming out of the derivation naturally. There is a time reversal. So this is something very interesting, and it's used in one of the advanced control techniques called adaptive inverse control. They use this property precisely. The idea is if you reverse if you have a sequence x of k like this, which goes down to here, is converging to 0, and you create a new sequence by mirroring with symmetric to this k equal to 0 line, you get a new sequence. This sequence goes like this. All right? It's no longer the usual case that we talked about. The sequence is all 0 for negative time index, but it has a specific form. Then its Z transform can be directly ruled out. And this is very useful in this scenario. In a lot of practical engineering applications, we obviously want the sequence to go to 0. That's a nice thing. And we can evaluate the Z transform very easily. In few applications, things can go wrong a little bit. There may be possibility that your sequence is going like this. So it's going up. And common engineering, we would think this is a bad thing, right? Because something is going wrong. Something is going to very big values. Then this time reversal technique can actually be used to help us find out the Z domain properties by looking at things just a little bit differently. So if you create a symmetric sequence with respect to this k equal to 0 line, and you look at this new sequence in this direction, then it's reducing. It's not going to infinity. So this new sequence, if you look from this direction, is reducing, is not increasing. So that's a basic idea, and the detailed techniques, how this is used, what kind of convenience is brought by this property, is out of the scope of this lecture, this class actually. It's a more advanced digital control concept. But this is a very useful property, and I use it personally in my research. Convolution. This is a fundamental relationship we want. We rely on actually in all the control analysis. In the continuous time integration, the convolution by integration is multiplication in Laplace domain. Similarly, if you replace integration by summation and you still consider this kind of convolution, fk minus j, so the summation is over j, k minus j, gj, then this convolution, if you do the z transform, is multiplication in the z domain. This is super helpful in any kind of control analysis. Let's say you have one controller and you have a second controller. And you have a sequence, let's say U1, okay? From this controller, you can identify what is the output, let's say U2, right? And then you can do one more time. You know the input U2 to C2, you can get, let's say, YK. This convolution property is super important in the sense that if I don't want to know U2, I just want to know what Y looks like, then we can we don't need to compute this step at all. We can just combine these, treat this as a large controller C1 times C2. This is the core of analyzing any block diagrams involving multiple steps of control algorithms. So that's the convolution property. And you had an exercise on Laplace domain convolution. The derivation for this one is very similar. Now, the initial value theorem and final value theorem, these are related to the Laplace domain theorems with a little bit of tweak. The initial value theorem, f0 is limit. So you want to know what happens at time t0, you go to infinity in the z domain. But the difference here is that it's just a z to infinity fz. It's because just by definition, fz is summation fk z negative k from 0 to infinity, and it's f0 times z to the power of 0, which is 1. So you just need to write it out and see very quickly. So you can keep adding terms. So if you want to know what is f0, you let z to infinity. Then you have z to the power of negative 1, which is 0. Negative 2 is 0. So all these are going to be 0. So that's how the initial value theorem can be quickly proved. There's no z hanging out. In the Laplace domain, it's f0 equal to limit s to infinity s f of s. This is the difference in the z domain. It's easier, I would say, in the z domain. The final value theorem is as follows. So the final value theorem is saying if you want to know what happens to your sequence at time infinity, just go with z go to equal to 1, and then evaluate z negative 1, d minus 1 times fz. Slightly different in the continuous time case as well. But when we talked about the DC gain, we talked about the concept. DC gain in continuous time is G evaluated at S equal to 0, right? And then when we talk about DC gain in the discrete time, it's Z evaluated at what? 1, right? So S equal to 0 sort of have a correspondence with Z equal to 1 in the discrete time case. In the continuous time, when we had f infinity is limit s go to 0, s f of s, you can see the concept is the transformed property times this one over here, s times fs. So the same thing here, you let z equal to 1 and then z minus 1 built inside. So there is a rigorous way to prove this formula, and there is a very intuitive concept behind it as well. Any questions? With these properties introduced, these are the common Z transform pairs. It's extending a little bit of what I wrote down here, so it covers more like what a sine looks like. So it's similar to a cosine, and then in the numerator it's slightly different. If you have scaling built in, this is using the property immediately. So if you scale your time sequence by a geometric sequence, then we talk about the property. It is replacing z by, so it's replacing z negative 1 with a z negative 1. So it's just a scaling of z in the z domain. Immediately using the one of the properties we just talked about, scaling in time. We talked about these. This one is time reversal, the property of time reversal that we talked about. This is what property? If I have k times a sequence, you have the time index time in the sequence, then it's similar to tft in the Laplace domain. So it's differentiation in the discrete time domain. So this is taking the derivative over this one. You can get this. This is a table that you can refer to from time to time. And most of the signals that we deal with are covered by this table. Let's take a quick break. So at the beginning, at the first lecture, I told you what the goal of this class is about. The goal of this class is to give you the tools to build a model, to analyze a model, and have the insight to work on control systems. And I want to also give you the concept or some practice about how to implement controllers. So this is the last aspect of how implement and analyzing controllers using modern tools. MATLAB is the tool over here, and you all have access. I think for you guys, MATLAB is free. For me, I have to pay. But it's a fantastic tool, and now I can run it not just on a computer, but I can run it on MATLAB and even cell phones. So they have made tremendous progress, although they charge me, but I'm willing to pay that. What I want to do now is to test some of the concepts that we have been talking about. So we talked about the transfer function. I want to show you how transfer function can be built in MATLAB. It's very easy. In transfer function, you have, let's do continuous time first. You can do s equal to tf, and then put the bracket inside, and s, to tell MATLAB, s is the s operator in Laplace domain. So you see it recognized as is a continuous time transfer function notation. Then you can do, let's say, G equal to, do we have some example over here? Let's do this example. Let's say G is 1 divided by S plus A. Let's say A is 2 divided by S plus, let's say B is 3. Then this is a transfer function. So we talked about the concept of DC gain, right? Which is what for this transfer function? It's going to be S equal to 0, which is 1 over 6. You can check by asking MATLAB what is the DC gain for G. It's 1 over 6. I think this is precisely 1 over 6, right? So it's 0.1667. So that's a match. And then you can do many things. For example, if you want to know the step response. So we show the picture over here. Let's check what is the step response for G. So it gives us the step response over here. What did we say the DC gain? It's 1 over 6. It's 0.1667. You see what is the final value here? 0.1667. So exactly, that's giving us the DC gain concept. All right, so that's for continuous time systems. So you can do a lot of more things. You can do, for example, the impulse response. What is the impulse response for G? Then this is the impulse. So if you hit a hammer to the system has an initial response and then it goes away, dies out for this particular system. So for discrete time, you can do the same thing. You can say D is the discrete time operator. So you know it's a discrete time system. We haven't talked about the sampling time yet. So this is unspecified. If I want to know, if I actually know how fast my discrete time sequence is updated, I can put that to MATLAB. Then we can do, let's do another. Let's say G, let me use a different one. Y equal to, I prefer X. X equals some example. Let's do the one here. Let's do the simple one. We talked about a geometric sequence. We talked about a step signal. Let's do a step first. X is a step. Let's see whether this is the case. So if I want to know the impulse response, oops. So this is a step, right? If your input is an impulse in the z domain, it's 1. So 1 times this transfer function z over z minus a minus 1. The output is z over z minus 1. So it's a step. So you see exactly. Yes?
Is there a physical meaning to the DC gain in the time domain?
It's exactly the same concept. If you apply an input that is a constant, let's say 1, your output is going to be a number. And I will show you right here with a different x. So let's do, this is z minus, I want to do 0.9 over 0.5. So this is a transfer function in z domain. Let's do the DC gain first. DC gain of x is when z equal to 1 is 20. And then if you do step x, then MATLAB gives us. It means I apply input with magnitude 1. Then you see the output. So after some time transient, it goes to precisely the DC gain 20. So 20 is a little bit difficult to see immediately. Let's do z minus 0.5. This should be easy enough. So the DC gain for this one is what? 1 over 0.5, which is 2. So this is exactly 2. What we derived over here, these are all valid. That's the MATLAB commands for analyzing continuous time and discrete time transfer functions. There are many more tools you can use.